I have the honor to introduce today Ulrich Schollwoeck from the University of Munich, and I'll say a few words about him and his area of interest. You heard a little bit down at the lobby, but I want to make some extra points. So Uli is a German citizen. He was educated in Munich, and then he got his extra education also in France, in Saclay, and then in Oxford. And then he turned back to the German academic system and climbed up to the rank of a full professor of theoretical physics at the University of Munich. He's also an avid Aspen visitor. He came 20 times to the Center of Physics, very active in our activities. His main area of interest is called strongly correlated electron systems, and that sounds very scary to people outside. Why would anybody be interested in electrons and their correlations? But this is actually probably one of the most fascinating areas of physics studied these days because of its complexity. So while we know a lot about the single electron behavior, we know how to solve the hydrogen atom very well, when you put a lot of electrons together, even the strongest computer can't really tackle the question of what's going to come out of that. What's going to come out of many electrons in a system, in metals, in systems where you have magnetism and superconductivity and very interesting resistivity and electronic behavior. All this is emergent phenomena. That means something that you could not predict a priori if you just looked at electrons by themselves, and if you looked even at 2 and 3 electrons. You won't be able to understand superconductors, for instance. So this area of physics has a limitation that there's very little we can actually predict and compute from basic principles. So what is done is people look at experiments and get ideas from it. And the ideas inspire new approaches to first to modeling and then to solve those models on the computer. So Ulrich Schollwoeck is probably one of the leaders, the world leaders, in taking complex problems of many electrons and turning them into algorithms that can actually predict what the experiments will give. And that's the main mission. But the side benefit is that while working on such complicated problems, ideas come out in designing numerical and algorithmic advances that affect many, many other areas of life. So I won't go on any further and let Uli take the stage. Thank you.
Well, good. Okay, well, thanks, Arthur, for this wonderful introduction. You did this so well that you could basically continue and give the talk. Well, welcome everybody here in the Villa Opera tonight, and join me, please, for our exploration of the psychology and the emotional life of quantum particles, what this will all be about today. Well, when you open the newspaper these days, you will find that quantums is all over the news. What you can find there is like, for example, Microsoft makes bet quantum computing is the next breakthrough, and so on and so forth. And this excitement of business and the media has also reached politics. For example, in June, Senator Harris of California introduced a bill to create an entity to support the development of quantum information science. And guess what? Just before Christmas, President Trump signed the National Quantum Initiative into law. So if these two agree on something, it's either going to be great or the biggest fad of the 21st century. So I'm not sure, I don't know, but what I can say for sure is that currently there's really a global gold rush going on. These quantum centers are mushrooming everywhere on this planet. I don't even want to go through this list, just to see this is a subset. And the Chinese at the moment say they want to top it all. They want to build the China Quantum Center in Hefei and invest $10 billion in that institute. So this thing is really big. And so you may wonder, why all this excitement today? So I ask another question. What do these 5 have in common? Apple, Amazon, Google, Facebook, Microsoft. Any idea? Don't be shy. So exactly, they have. It's large. I heard large and I heard information. So They are, or were at least in mid-18, the 5 US companies with the largest market capitalization. On the other hand, these companies all make their money based on computer hardware and software. And there's one more thing, because actually what they do is they make money with quantum physics, because all modern information technology is built on transistors. There's been a long way from the first transistor in 47 to a modern chip of Intel, which has 2.3 billion transistors on chip. And transistors are fundamentally quantum. So quantum is around in our world everywhere. So you may wonder why actually the excitement today. And the reason for that is that so far our quantum technology is using two, and I should say only two, quantum features. And the one thing is something called particle-wave duality. And you can see on the left a picture of NASA, which shows a surface where atoms have been arranged in the form of a coral. And inside the coral there's electrons. And the electrons, which are particles, they look like waves. These are exactly the waves which you get if you knock on a glass of water. You have certainly seen that in your life. And this is not just an artist's impression. What you can also see is how you actually build these quantum corals and how then this wave structure emerges as soon as the particle is locked in. This is the one feature a transistor uses. And the other feature is something we call quantum statistics. This is something a bit more abstract, which tells us that particles come in two varieties. The ones are called bosons, and the other ones are called fermions. And electrons, which are of interest to us today here, they are fermions. And these particles are the absolute individualists. Quantum particles can be in different states. We call them quantum levels. And these fermions absolutely don't want that two of them are in exactly the same quantum level or state. They hate that absolutely. Perfect individualists. And this was discovered about 100 years ago by Wolfgang Pauli. And all what we have today is built on that. But what we are not using so far is something called entanglement. And this is probably the most exciting or weirdest phenomenon of quantum physics. And to explain it to you, I was looking for pictures, and that's what I found. Stuff like this I found on the web, these mysterious atoms, these spaghetti or these entangled hearts. I also found a CD cover, Alanis Morissette, Flavors of Entanglement. So that was not exactly what I was looking for. So I had to think myself, and what I came up with is that entanglement is the picture of NASA, which I already showed to you, and this. So to get more into that, let's analyze these pictures. Before we get to the second one, we first have to understand the first one more properly. Okay, what we have is, if you look at that, this is a piano chord. Unfortunately, there's no piano on stage, so I would have played it. This is simply CEG, and that's a sound wave that comes with CEG. And what really happens on the piano is that this is a superposition of three sounds, namely the key C, E, and G. Well, and this looks much simpler. And quantum particles, being waves at the same time, they can do the same thing. They can be added together. That you can form, we call this superpositions of waves. And like on the piano, where of course you can play one sound louder than the other one, you have to say how loud you play each individual note on the piano. And that's what's going on in these quantum particles. So the other thing is now this picture with these quantum eggs. Now, eggs, as you know, come in two different states. They are either brown or white. And now I ask the question, in how many ways can I put eggs into an egg carton? This depends on the number of ditches. So if I had an egg carton with a single ditch, there would be just two ways of doing it, either brown or white. So as soon as you have two ditches, there are four ways of doing it. 2 ways for the first ditch, brown or white, and 2 ways of doing it for the second ditch. And this goes on as long as you want, and the numbers grow enormously. So if you had an egg carton of 64 ditches, I mean 64 eggs, that's not really that much, the number of configurations that you get stands at 18 million trillion configurations. I hope I got that right. But just to compare, this afternoon the US national debt was standing at almost $22 trillion, which by comparison is absolutely negligible, so you don't have to be worried at all. Okay, so there are lots of these configurations, but ultimately if you have an egg carton at home, there is only one of them. So you can easily write it down like brown, 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 white, and so on and so forth. So basically it's one line of text. If, however, these eggs are quantum, and they can be in any of these configurations, you have to say for each of them how important it is. You have to write this down in books, say, and the number of books you would need to print the information contained in such a configuration, if it were quantum, would be 1,000 trillion books, something like this. So this already gives you an idea why quantum physics, as soon as we are talking about more than a few particles, becomes incredibly complex and rich. Okay, so now we have to translate from the quantum eggs into the real world of physics. And the way physicists do that, they write it the following way. So this is a brown egg and a white egg, and physicists simply like to write this as a so-called state. The world has a brown egg and a white egg, and the distinctive quality is its color. Now, on the other hand, what we are really interested in is electrons, and electrons have a similar property. It's called spin. It's their tendency to rotate clockwise or counterclockwise, and this we denote by arrows pointing up or down. And then the state for the electrons looks like an up arrow, and the second electron has a down arrow, but ultimately this is nothing else but saying that I have a brown and a white egg. It's not more complicated. Okay, and now we have all the ingredients we need to come up with this entanglement, and we do that on the next slide, where we simply now do the simplest thing that you can do. We consider two of these possible configurations just for two eggs, like brown and white, or white and brown, and we add them, like the sound of the piano. We can add that up, and now something really weird is happening. If you now ask, what is the color of the first egg? In real life, you would say, well, it's brown or white. And here, you are absolutely unable to say anything, because it's somehow brown and white at the same time. So as far as the first egg individually is concerned, you have absolutely no information whatsoever. On the other hand, if you know what the color of egg 1 is, you can 100% sure say what is the color of egg 2. So if the first egg is brown, here you would immediately know that the second egg has to be white. And if the first egg were white, you would immediately know that the second egg is brown. And now imagine you bring these eggs far apart, or these electrons far apart. Then all you can say about them would be information that is related to something that is non-local in this world. And this is a very weird feature, and this is what we call entanglement, this non-locality of information, which is totally unlike anything we know, because we would say this box is black, this here is brown. So everything is quite separate and local. And here, all of a sudden, essentially everything we are saying about the world is becoming non-local. And the big question of the day is to look at this non-locality of quantum information, which has no counterpart in our classical world, and ask the question, can we use this non-locality of quantum information for inventing new ways of information processing? One of these new ways would, of course, be the quantum computer, which maybe is a bit far ahead in the future. We will see. But even today, there are already applications that do work. On the one hand, we have quantum cryptography, where at the moment it seems that China is having a lead, and this is, of course, why this quantum initiative has been founded, I think, ultimately. And the other thing which is working already is, I think at least the older ones here in the audience will recognize that this is Captain Kirk of Star Trek being beamed back from some planet. This guy didn't really like it so much down there. We can do this not with humans, but we can do it with particles. So this is already working. What the guys... This week in Aspen, we have our conference in the Aspen Center for Physics. What we are interested in is rather asking, could all this be relevant also, as Asa already said, could this be relevant to materials? We like to call this many-body systems. And that's indeed the case. And I want to walk you now through this physics, or at least some aspects of it. Now, let's look at a piece of matter. That's a piece of iron. And if we are interested, say, like in its electrical properties, we have, of course, to look at the electrons. And in the first simple picture, we could envisage that these electrons are simply kind of moving around in a box, and they are bumping into each other, interacting with each other. And what this means by getting sort of like to interact with each other, they will build up an enormous amount of entanglement and an enormous amount of correlation. Correlation meaning how what particle 1 is doing is related to what some other particle is doing. That's something that actually also exists in the world outside quantum physics. But, I mean, the point is there are so many of these electrons that this is becoming hideously complicated. But a weird feature of quantum physics is helping us to understand this. And actually thinking about it, this feature is not so weird at all. Let's turn to a typical Aspen situation, namely that you find yourself here at the corner of Main Street and 5th Street, and there's a skier with his skis on his back and asks you, where's the gondola? So what do you say? Well, the gondola, as you all know, here is down here. Do you say, well, go straight this way as the arrow flies? Well, that's probably not going to work. What's not going to work either is to say, well, head straight east and then head straight south. That's all not going to work. But what you are going to do is something what physicists would call is you would do a change of representation. Namely that you would somehow rotate the map, and then you would say, well, simply follow Main Street, and once you reach Hunter Street, go south. So in some sense, we would, of course, say we go from the directions of north-south, we go to the grid of Aspen. Physicists say this is change of representation, and everything becomes much easier. And in fact, you do this all the time, because once your skier gets onto the gondola, he will get out the ski map of Aspen Mountain, and what you can see there, that what happens is that now south is now suddenly facing up, and north is facing down. This is unlike any other map you are using, like look at a New York street map or anything. It's always north is up and south is down. So this is just because it's more convenient for understanding how Aspen Mountain is set up. So this is what we are going to do now as well for our quantum particles. So what I will do is I will revert to that picture that I can understand particles also as waves. And this is kind of a cartoon version now of the very complicated wave structure of these electrons. And now I want to break this into pieces which I can understand. And there are two ways I could imagine. Well, there's certainly many more. But one way would, of course, be to say, well, let me construct this bumpy structure from a large sequence of individual bumps, as you can see it here. But you see there will be many, many of these bumps. It's much more convenient to understand that this is actually a sum of waves. And in a similar way to that, physicists have understood that thinking about a metal or so, it's probably much better to understand everything as a superposition of waves. And that's what we're going to do on the next slide. And we represent each of these waves, it's too complicated to draw by a straight line. Each of these straight lines corresponds to a different wave in which these quantum particles can be. And then we learned that these electrons, they are such fermions, these individualists, they just want to be one of them each in such a level, not two or more of them. So this is sort of like a relatively simple picture, but the problem, of course, here is these guys, they don't want to arrange themselves just like this, but of course they could also arrange themselves like this, like this, like this. And you are back to this incredibly large number of configurations which we have already seen for our quantum eggs. And the wonderful thing, it turns out, is that for semiconductors, which is the basis of our information technology these days, there it turns out that very often one configuration, say this one, is already good enough to explain almost everything you need to get the technology working. And this is, of course, a wonderful feature, but on the other hand, because this superposition idea is lacking, because you have only one configuration, not all the others, there is also no entanglement in such a situation. This is, on the one hand, very simple, but it lacks what makes quantum physics so weird. Okay, and there is, of course, also materials on this planet where this simple picture does not work, and these are the strongly correlated materials we are interested in. And what is happening in such materials is that many of these individual configurations start mattering. For example, what you can see here, this is a symbol for the lattice structure of a crystal, and in this crystal the electrons are moving, so these are these little blue guys, and sort of like this one wants to hop there, he can do this. Then this guy, but you also might want to hop here, but there's also another electron sitting, and as they hate sitting together, this is forbidden, this is not possible. And this is, of course, happening on the scale not of 2 electrons, but myriads of them. So what they really start doing is playing an intricate dance, which we have to follow. And in case you think this is rather arcane, I put up a periodic system here, or periodic table, I think it's called. Yes, periodic table. And all the elements which are put here in red, they are of that sort typically. And this contains really important stuff like copper, iron, cobalt, and so on and so forth. Basically, all magnets we are using are of that category. High temperature superconductors, which technologically might be very important at one day, are in that category. And also the famous rare earths, which become industrially more and more important, are in this category. I'm just listing a few of them. For example, neodymium is in most small devices these days when you want to have a magnet, because this is the element that produces the strongest magnets we know. Or if you are up on Aspen Mountain and you have sunglasses shades, and if they are pink, because they are very fashionable, you can be sure that they contain erbium. This is the material which you use to make them look pink. Okay, so this is the stuff we are interested in, and a point which we have here is that all this is very complicated. Asa already mentioned it. There's extremely complicated behavior coming up, and so we must admit that today we are unable to solve the physics of such materials in all and every detail. But often in life, you know, it's not so important to understand each and every detail, but just to get the essence right. And to understand this, well, I show you this here. Okay? So whether you voted for him or not doesn't matter. Everyone in the audience immediately knows who this is, despite the fact that it's kind of a simplification. Okay, and that's the same thing we are trying in our research. Like, I'm currently interested in this structure here, and that picture is already an incredible simplification, but we go even further. We make things even simpler, like we represent the fact that a crystal has a periodic structure just by something like this. This is a lattice, and the electrons can sit at various places, and instead of moving around just as what they like to do, is they can only hop from one side to the next. This is our cartoon of their motion. And they have a Coulomb repulsion, meaning that they are charged, and charges repel each other. So we say, well, they repel each other only if they are sitting really very close to each other. So this is really dumbing down somehow the entire physics of the problem. And so the question comes up, on the one hand, is this good enough? Does this capture what we are really interested in? And on the other hand, is it simple enough that we can actually solve even these cartoon problems? And for solving these cartoon problems, we have come up with essentially two strategies. The one is what we call classical simulation. This is that we take a present-day computer and try to let it play these quantum dances, what these particles like to do. This, as we have seen, is likely to become very inefficient because of the enormous amount of different configurations that exist for these particles. On the other hand, this is an idea that goes back to Richard Feynman in 1982. What we can do nowadays is we can build quantum systems which we understand very well, which are made to simulate the behavior of the system which we really would like to understand. This is something that's working, and I will show examples for both of that. And, well, to see what the problems of the classical simulation are, let me go back to our eggs. And the problem is that in real life, in real matter, the number of quantum eggs or electrons is something like 10 to the power 23, so 1 and 23 zeros. This is quite a bit more than the 64, which we have seen beforehand, which already gave this enormous amount of configurations. So if you wanted to store, I spoke about these 1,000 trillion books, we would nowadays, of course, use hard disks. And if you wanted to store the information in one such configuration, just for 64x/electrons, you would need about 140 billion, did I get it right? 140 billion gigabytes. And the entire storage on Earth today is about 3,000 billion gigabytes. So this very simple problem would already take up 5% of the entire storage we have on Earth. And this is far away from what we would really like to understand. And what we have managed to work out over the last decades is really methods of compressing this enormous amount of information so that nowadays we would store that information instead of these 140 billion gigabytes in just 10 megabytes. So, and this is actually what makes these classical simulations possible. But this entanglement, which depends on this number of configurations, if it gets really large, this comes to a limit. We will see examples of that in a second. But nevertheless, we can understand quite a lot of the properties of these quantum particles, and I thought I would like to organize it a little bit in terms of their psychology. So, as I've told you, normally these particles are extreme individualists. They want to stay on their own, they move around and basically keep away from everyone else. But once you put them into a one-dimensional world, they change their behavior completely. They turn into this other type of particle, which I mentioned, these bosons, which quite on the contrary, they don't want to be individualists. They want to do everyone the same thing as everyone else. Well, sometimes it's a little bit forced, like you could imagine that to be a traffic jam on a freeway in Los Angeles, so one car behind the other one, so you're really forced into a collective behavior. But they do it on their own. But this, in some sense, it seems to distort their personalities nevertheless, because they develop split personalities because of that. And this is a very common feature which we observe now in many different circumstances. Just take this electron here. It has an electric charge, and it has this degree of freedom called spin that it's turning around. And once it ends up in this collective behavior, what happens in this particular case is that they start behaving in a weird way as if they were two different particles which have nothing to do with each other, where one of them carries all the charge and the other one carries all the spin. Let me explain that using a cartoon. So, this is the traffic jam I just talked about, and here are these particles arranged with their spins. They have a tendency that if they are locked up together, that they like often to arrange themselves in this up-down pattern. And now what you do is you kick out one of them, like here. So a missing electron is there. And what now can happen is that one of these, like in a traffic jam, you can now move up car by car, so the hole moves to the left, just like this. On the other hand, what you see now, there's now a mismatch. They point both in the same direction, which they do not like to do. So what they can do reacting to this is they can flip their position or basically invert their orientation. But as you see, this just means that this kind of two spins pointing the same direction is being transported. And that actually is sort of like a totally separate behavior, and we refer to these guys as spin-ons, where we have this excess of spin, and holons, where we have this missing charge. So, and this behavior actually explains why all this happens only in one dimension, because you can play the same game also in a two-dimensional setup, where you split them up, like in this hole and this spin-on. But what happens if you do that is that in between this arrangement of spins, this up and down arrangement, this is maintained, but now it's out of sync with the up-down, which happens up here, because they also would like to point in different directions, and they point all in the same directions. So this is becoming very unpleasant for them, costs them lots of energy, and so they don't do this, and this is why this weird splitting of personality, or we call it spin-charge separation, is only happening in one dimension. Okay, so now you may believe this guy is telling all sorts of weird stories. Do I have to believe that? And honestly, you don't have to believe this cartoon. If you think more closely about it, it may create, you will see its problems actually. But what we can do with our simulational methods is we can now simply look at the real quantum system and check whether this splitting of personality is really happening. And so what's happening here in this movie, which I'm going to show, is this is a situation where you have lots of electrons on a chain. Now we insert an additional one. This brings in extra charge. Charge is here in red, and it brings in extra spin, because it has this one way of pointing, here in the center. And now what happens? I'll play the movie twice or 3 times. So this excess is being kind of removed. It spreads out. And what you can see is there's this charge bump moving left and right at a certain velocity. But what you can also see in the replay, that there's also bumps moving into the 2 directions, but at a totally different velocity than the charge. So this is really how you would also observe in an experiment that there is this separation of spin and charge, and it's only happening in 1 dimension. So what we have seen now is that psychologically they have a very interesting collective behavior, but even when you go to the kind of more private life of these particles, interesting stuff is going to happen. This brings us back to the entanglement. So I try to draw entanglement in the following way. That here I have 6 particles, 6 electrons, and one thing we know nowadays that you can pair up 2 of them to form something which is called a maximally entangled state, like the eggs which I showed beforehand, where the information is maximally non-locally distributed between these 2 particles. You can say very little about each of them individually, but you can basically say everything about how they are kind of cooperating. This is for the physicists. I mean, they know this formula anyways. Okay, so at first sight, this thing that they can only pair up just 2 of them is something we call monogamy of entanglement. And so these particles look like leading a very virtuous lifestyle. But in reality, what they do is they like to switch partners all the time. Because, I mean, there's no reason why this particle should only pair up with this one. Why not with the other neighbor? So they switch about, say, 1 billion or even more times a second. So the best thing you can say about them is not that they are monogamous, but at best you would call them serial monogamists. And as in real life, this property of being serial monogamous creates a lot of mess, emotional mess. So let's see that on the next slide. What happens is the following. Imagine you have a bunch of these particles sitting along a 1-dimensional row. For the moment, they are paired up peacefully. Don't do anything. So to get a little bit excitement into their life, you kick one of these couples, namely this one, and then I propose to you a scenario. Honestly, I say right away, that's not really what is happening in nature exactly like this, but we could set it up like this nowadays. So I give a kick to that. So they are split up. So the shock wave of this is propagating through the system. So the next thing that is happening is the next couples are breaking up left and right. In the meantime, the first couple has decided that it was not so bad after all. They get back together, whereas those, they are so totally annoyed that they look for new partners. And the next new free partner is for this particle, of course, not that one. They are not talking to each other anymore, but it's that one over there. And the other one, of course, pairs up with this one. So you see they create entanglement by this. And of course, the whole game continues. So these pair up and these pair up. So if that is what happened after a kick, honestly, it's not happening, but this is kind of a scenario you could imagine. What you would have in that case is that this entanglement grows linearly in time because there's more and more particles that form these pairs, you know, across a boundary. At the beginning, there was only one pair across this boundary. Now it's many pairs across this boundary. And they do that until basically they have run out of space. Everyone has found a new partner. Now, the reality is that this is, in fact, the worst case scenario. But we can, and for this kick, it's actually much weaker. But we can realize this in many experiments these days, And this is just one typical curve from a computer experiment. We don't have to go into the details. The important thing is just to see that as time goes on, this entanglement is growing linearly in time. And at some point, for any of the scenarios considered in this picture, it saturates simply because they have run out of new partners for getting entangled with. The point is, if there is this enormous amount of entanglement, the system becomes extremely non-classical, and the simulation on our classical computer becomes essentially impossible. This is where people like me who do such simulations are at the end of their wisdom. But what we have in this situation is now these quantum simulators, real quantum systems built by experimentalists. And one setup which is extremely popular these days is to create this cartoon version of reality, which I already talked about, by light. So they build crystals, but not from real matter, but from interfering laser beams. And in these crystals of light, they capture atoms, and these atoms can then do exactly the same thing that I wanted the electrons to do. They can hop, and if they sit on the same side, they repel each other. So this system actually, although it's atoms, simulates what electrons are doing. And the wonderful thing is that you can play with all the parameters. So this is the dream of an experimentalist, that he can basically ask any question he wants to that system. So what does this look like in real life? So these experiments are now done in many places on this planet. I think the closest from here would be Boulder. And this is one of the experiments in Innsbruck. You see lots of optical tables, but the actual heart of the setup, and this is a movie from my colleague Emanuel Bloch at the University of Munich, is something called a magneto-optical trap. I mean, these atoms don't really want to do this simulation for you. In principle, what they would like to do is to move around freely. And what you will see in this movie, and I think this is incredibly exciting, because decades ago, who would have thought that you can really see these atoms? Like, and pay attention to white clouds inside. So let me play this. So you see, this is a cloud of atoms, a few 100,000. And if you switch off this trap, they are simply flying apart. Let's look at this movie kind of. I don't know exactly what's going on here from an experimental point of view, where it's kind of, you will see it's trying to emit these rays. I don't know what's going on here. What you really understand, or easily understand, is when they fly apart when you switch this trap off. So this is really a cloud of atoms flying apart. So these setups are now being used to study these complicated quantum phenomena. And one which perhaps it's quite a bit old, but I think it's interesting in the context of Aspen, is, of course, the big question which you all have here is the important phase transition between ice and snow, and on the one hand, and water on the other hand, at 0 degrees centigrade, or was it 35 Fahrenheit? So, and they can do similar things in the quantum world with these quantum simulators. For example, what you have here is this is one particular kind of quantum system which you recognize by this special pattern, and they give it a kick to basically transform it into another one. And this is what then should happen. This is what the new state of matter, like water, would look like in that experiment. But then something really wild is happening. The original quantum system is coming back. And in fact, this is the real movie from the experiment where you see this quantum system coming back again and again. This, however, that a quantum system, after being disturbed, comes back to its original state, this depends on extremely special circumstances which were realized in that experiment. What is much more natural, and the current focus of research, is something called thermalization in the language of physicists, or they say the particles relax. So what does this mean? Well, this is something which you can do back at home or at your hotel, which is a kitchen sink experiment. You take a glass of water, you insert a drop of ink, and then what happens is that the ink will spread out. It will form incredibly beautiful and complex filaments of ink. And then after some time has elapsed, if you wait long enough, the picture will again become very simple, because you will just have this bluish hue of the ink that has completely dissolved in water. And that is what we call thermalized, that basically all the structure has disappeared and basically everything has averaged out in some sense. This is what happens, for example, also in nature if you take a piece of ice and let it melt into water. Okay, and this is what we would like to understand. And in the first experiments, basically we did in such circumstances, one which I was involved in, just served to understand such behavior in extremely simple cases, which at first sight may look a little bit boring, but we had to understand how this machinery is actually working. So what we did was we put atoms in there on every second lattice side. This is for them a totally unnatural state of life. They want to walk around and spread evenly across the system. So what you expect that ultimately they start bumping into each other and spread out at a density of, say, 1/2 across the entire lattice. So the colors look quite similar, but here you should really not think that the number of atoms has doubled, but it's just that they have spread out, and on average, half an atom is sitting on each lattice side. Quantum mechanically, this is easily possible. So in these first experiments, one could really see that all this is working. So from a theoretical point of view, what you can predict is that as they start doing this thermalization, life becomes much more interesting and complicated for them because they get correlated. By bumping into each other, their behavior becomes dependent on each other, and depending on how strong their interaction is, this correlation may take different values. This is not so important here, but what is important is that both the classical computer simulations, which is what people like I do, and the experiment, this is a special way of seeing what these particles do, are in excellent agreement. So what we can do nowadays, we can really see how, as these systems thermalize, how they build up their quantum correlation among each other. The particles build up their correlation among each other. And this is basically what the quantum simulator says, what is going to happen. And this is what the classical simulation says. So they are in extremely good agreement. The one point, however, is, and this I do not, as a theoretician, I do not show on this picture, is that the experiment that goes on all the time, basically as long as you want, I don't know, to the gondola or anywhere, whereas the classical simulation we do, because of this entanglement, stops at some point. It simply becomes too complicated for a classical computer. Okay, so this may seem a little bit boring. For us at that time it was quite exciting because it gauged the precision of the methods, but you can apply it to more interesting questions of life. So, and one more interesting question of life is, of course, jealousy. And jealousy is not just a property of human beings, but I discovered that it also happens for these quantum eggs. And so the question is, of course, jealousy is not a good feeling. What can we do about it? And one way of dealing with jealousy might, of course, be forgetting. Now, forgetting is a difficult issue because quantum physics tells us that all is remembered forever. Nothing is ever forgotten. In some sense, this experiment where the original quantum state came back is a kind of a metaphor for that. On the other hand, the experience with the drop of ink which dissolved in water would tell us it's different. Nature says, nature forgets. Like once you have this situation here where the ink has completely dissolved, there is no way of saying where and when exactly you inserted that drop of ink into the glass of water. This information is simply completely lost. So there is really a deep foundational question of physics behind it about information and memory. And actually, that brings us to a totally different field of physics. I mean, far away from the electrons in a piece of metal, which would be black holes. I mean, what you can see here is a black hole moving in front of a faraway galaxy, and what you can see in this animation is how it distorts the light that comes from this faraway galaxy. But the important point for us is that you can see a lot. The one thing you cannot see is the black hole, because the black hole, as you all know, it eats up all matter, it eats up all radiation, which is then removed from the universe, so to say, and in some sense what it does, it eats up information. All the information that comes along with this matter, with this radiation, is eaten up by the black hole. And this observation has actually created a huge debate in physics between very famous physicists. I think all of you know Stephen Hawking on the left, but there's also Kip Thorne, Nobel laureate from Caltech, John Preskill also from Caltech, Leonard Susskind from Stanford, and they had this big battle about whether this information is actually totally lost, which would be a problem for quantum physics because it says it's not lost, and these other guys say, no, the information comes back. And what this debate was about something called Hawking radiation, which is that these black holes are not totally black, but they emit a tiny little bit of radiation over time. And Hawking was of the opinion that this radiation does not carry the information back, and these guys say, no, it does. And currently the agreement seems to be that the information does come back. And so quantum mechanics seems to be saved. But then if this is true, a second problem emerges, because there's another big tenet of quantum physics which says that you cannot copy a quantum system perfectly. This is something called quantum cloning, and there's a theorem which is called no cloning theorem, which says this is absolutely impossible. But with the help of black holes, you might do the following. There are two physicists, Alice and Bob, and Alice is the proud owner of a quantum state. We like to write them psi or so. And what Alice does, I don't know why, but she jumps into the black hole and takes the state with her. I mean, it's pretty mad, but she does it nevertheless. Bob waits outside, and he observes this Hawking radiation. Now, the Hawking radiation brings back the information about the quantum state. So what Bob does is he reconstructs the quantum state from this information, and once he has it, he jumps into the black hole as well. And now, at the right moment, I mean, they are just crazy, but at the right moment, Alice sends the information of her quantum state to Bob as he is falling into the black hole. And if that happens at the right moment, Bob will have both his quantum state and the exact copy of Alice. Now, that would, of course, violate this quantum no cloning theorem. Now, all this play between Alice and Bob is a really delicate question of timing. And what the cosmologists found out is that it all depends whether this would be possible in principle or not, whether about something which is called information scrambling. They say, okay, information is not lost. It's always there, but it may be that it's so widely distributed among many different quantum particles that effectively you have no means whatsoever of recovering it. This is a bit like in this picture of the ink here, where of course you could think about, you could pull this back together into the drop of ink, but effectively you can't. And what they also found out is to forbid this quantum cloning, what you need is that there's a speed limit on this scrambling of information. And so they came up with a conjecture that there is indeed a scrambling speed limit, which basically protects that quantum mechanics is correct, and that black holes are actually getting closest to it. They are the fastest scramblers in the universe. Don't ask me why, this is really beyond me. This has been done by incredibly smart people in cosmology. But you see, these are all conjectures. And the problem is, as one or two colleagues formulated it, that experiments that can probe the quantum dynamics of black holes are currently out of reach. And I think it's pretty clear that this is going to stay like this for the remaining age of the universe. So the question is whether our rather simple models on planet Earth, whether they could help us in solving this problem about the quantum scrambling. And in fact, this scrambling is something you already know, because it's nothing else in the quantum world what in our classical world we know as the butterfly effect. You know, the thing where a butterfly flips his wing, and say in Brazil, and then there's at some point, because of that, a tornado in Texas. well, as you can see it here on this picture. In a more mathematical language, it means that you may have particles which start out behaving almost exactly in the same fashion. So you can really not distinguish it. And nevertheless, they end up very far apart as time is evolving. This is what the foundational idea of chaos theory. Now, the question is there an analog in quantum physics? And indeed there is, and physicists have come up with a very wild object. I'll show it. I mean, this is called an OTOC, an out-of-time order correlator. And this looks difficult not just to lay people, but this looks difficult to physicists as well, believe me. And so we have, but this is what we would have to understand in order to come up with a better understanding of the scrambling of information. When does it actually become inaccessible despite still being there? And experimentalists have already come up with the first ideas of building such simulators for this question. And in Boulder, actually, there's an experiment which is one of the best getting close to it. But I think we are not really yet there. And one of the main problems is that this simulator has to be able to simulate quantum systems like going forward and backward in time. This sounds weird, is actually possible, but is very, very difficult. So for the time being, and we are really talking about research being carried out these days or in the last 12 months or so, we are really back to the point where we have to rely on these classical simulations. And what is happening is that it's an extremely rich and exciting picture of the dynamics of quantum particles and their memory is emerging. Because what we originally thought is that the decisive point, okay, I have to explain this. This is actually a paper from a friend of mine from Munich. He's here in the audience. That sort of like you have a quantum system, you give it a kick at some point, and then you see how this kick and the information associated with it spreads over the system in time. And normally you have a kind of a velocity at which such a kick propagates, like a sound velocity when you have an explosion and the sound propagates. We call this the light cone. But in fact, the information that is being transported with this light cone is being scrambled at a much smaller speed, but it's still happening relatively fast. And the fact that it gets thermalized, that everything gets totally washed out, that happens on a time scale which is much, much, much slower. So it's orders of magnitudes larger until you arrive at the picture, say, of the ink, which has been completely dissolved. The information has already been scrambled once, sort of like the filaments look like this. So this is an extremely exciting field of research which is currently going on about how long is actually the memory of these particles. But given the limited amount of time and your patience, I think at the moment it's time to sum up for the moment what we now know about the psychology of our quantum particles. So what we know is that these fermions, or electrons as an example, they are fierce individualists that may form these flash mobs. That's what we have seen. We have also seen that they may develop split personalities, this spin charge separation. On the other hand, we have also seen that they're inveterate serial monogamists. That's perhaps their most foundational property. They keep going at that before they don't give up before the maximum amount of mess or entanglement is created. They're extremely good at covering their tracks. Our classical computers cannot follow their behavior. This is totally impossible for us. As a collective, as a group, they never forget anything at all that has happened. But fortunately for them, I guess, their individual memories are relatively short. The information has been so much distributed that individually they don't really remember what has been going on. And I think we are only at the beginning of recognizing sort of like the very rich life and behavior of these quantum particles as soon as they're acting as a group, not just single particles, but many of them, the emergent properties that Asa alluded to in the introduction. And for me, what remains to do is to conclude with the words of Richard Feynman, which I slightly adapted. There should be poets singing about this, but there aren't. So you had to listen to this evening lecture. Thank you very much for your attention.
We take questions from the audience?
Yes.
So what does this all mean? And why is the government, everyone spending billions of dollars and research and the government and what you did in the beginning? What are they trying at the end to have a practical something?
Yeah, I mean, okay, so I was asked to repeat all questions that come from the audience so that everyone can hear it. So the question was, what does it all mean? Which is, of course, a very broad question, which was then narrowed down a little bit. Why is the government spending billions on that? Well, this is actually a very difficult question. I think it's relatively easy when it comes to simple applications like this quantum cryptography. I mean, there I think it should be pretty obvious because quantum cryptography is a way of encoding information which is unbreakable. And that's, of course, the dream of every government to transmit secret information without being exposed at some point. So, but this is, to be honest, not the behavior of these systems I've showed today, because for quantum cryptography, you're actually looking typically at pairs of particles, and then many of these pairs, but they don't have anything to do with each other. I think this is why the government is spending lots of money on that. The second reason is, and this is where it's getting on more difficult ground, is the hope that a quantum computer would come about. The quantum computer would be an engine that would be able to solve certain problems incredibly more efficiently than any classical computer. I mean, you got a hunch of that when you looked at this quantum simulator, which, being a quantum device, can simply simulate quantum physics and do something very complicated, which a classical computer can't. So this is why Google, Microsoft, IBM, they are spending a lot of money, because they, of course, they fear if some of the competitors manages to build such a quantum computer, it will simply outperform their machines, because it's in a completely different class. You know, it's not just a better computer, it's something totally different. And you don't want to lose that race. I think there's mainly the fear of losing the race. Whether this will be practical in the next few decades remains to be seen. I mean, there are better experts for that around in the audience, but I have my little doubts about it. What for this here is, I want to be honest, it's the simple joy of understanding some of the most fundamental questions of physics, like this question of how quantum systems thermalize, how they reach an equilibrium, how all this happens, how information is stored locally and non-locally. These are foundational questions of physics, which we have to try to understand for at least 100 years. And this seems to be a moment in time where we are really making progress in that direction. So it's, how should I say, it's this research good for nothing. But I'm proud of that. Okay, so now there are lots of further questions. Should we start in the front and work our way back? Is that okay? Okay.
Sounds a lot like entropy. How are you going to put this entropy back together again if you have
this is, yeah.
Ink in the jar, all of that.
Yeah, the question, just to repeat it, it's kind of the issue about the relationship between the entanglement and the information that is associated with it and entropy. In fact, this is a very deep insight that was made in physics a couple of decades ago, that entropy, the tendency that the universe gets more and more disordered, and information are basically more or less the same thing. And indeed, what do you say, you can't put it back into the jar, yeah? So like entropy, like this growth of disorder in sort of like in a typical physical system, like as you experience it every day, or if you look at your home and everything gets more and more disordered, the same is true here. Once these systems have become fully entangled, it's essentially impossible to put them back together in their original separate form. I mean, you can do this with lots of force, but then you lose essentially what they were about. Yeah, that's definitely true. It's closely related to the issue of entropy.
Why do particles entangle? And is the strength of the entanglement, does it vary?
Why do particles entangle, and whether the strength of the entanglement varies? The second question is perhaps easier to answer. Yes, it varies, because, how should I explain this the best way? this monogamy of entanglement is basically an upper bound. It just tells them that it just says that the maximum amount a particle can get entangled with someone else is what I showed. But in principle, it can be anything that is weaker, because, for example, if you look at these quantum eggs and you can experimentally put them in just one of these configurations, then they are not entangled at all, for instance. So it depends. Now the question is, why do they like to get entangled? Well, this is simply the fact that the quantum dynamics of these particles creates informational connections across larger and larger distances when they sort of bump into each other. So this is why there is a natural tendency that this is going to grow over time. Yeah. The natural state of nature is actually that they are maximally entangled, but sort of like we are as humans, we are actually in some sense very organized structures. So for us, what is very special looks very normal. For nature at large, big entanglement is the norm.
How can you use quantum to encode information if you can't tell them what to do?
Well, the question was how we can use quantum physics to encode information if we are not able to tell them what to do. Well, actually, no, we are able to tell them what to do. In what these colleagues as a theoretician, I can, of course, make all these big claims, but ultimately experiment is the arbiter of all that's going on. And the experimentalists, they are able now to control these quantum systems to an extremely high degree, and actually, imagine we had this superposition of these two eggs, like brown and white. So it seems we've seen that the properties of the second egg depended on the ones of the first egg. And imagine you bring them very far apart, and what you can really show in experiment, if you then change the properties, say, of the first egg in some weird way, you can do that. The properties of the second egg far away, they change with that. This is exactly how this quantum teleportation business or quantum cryptography business is actually working. We have this under control, at least for small amounts of particles.
Yeah. You made the statement that it can be used for cryptography and likely not be decrypted.
Yeah.
So I can understand from your presentation today how encryption might happen. I can think about that.
Mm-hmm.
But I'm assuming that somewhere it's decrypted once it's been transmitted.
Yeah.
And I'm assuming if you can decrypt it, then the statement that I can never decrypt it is hard for me to think about. It might be difficult for me to do, but to say...
Now, this is a really good question about how this cryptography actually works. Now, this sort of it's a very special kind of cryptography which goes back, I think, to a guy called Vernon in World War I. You see, cryptography would be perfect and totally unbreakable by someone else if you had something which is called a one-pad cipher. I hope I got the word right, which is you have a key. You always have a key to decrypt it, but the problem is sharing the key, because you use it to encrypt the information and you have to get it to someone else to decrypt it. And the problem is, of course, always that the transmitter might be a traitor or the information gets stolen. And the point is, of course, everyone can decrypt the information. The signal is being sent publicly, so to say. What you want to ensure in quantum cryptography is that the key, which you generate anew in a different one for each and every message, and this is what makes it unbreakable, that you get that transmitted in a way that no one else can access it. And this is ensured in this quantum cryptography by the fact that there is a feature of quantum mechanics which I did not talk about, is that if you look at these quantum states, in some sense you destroy these superpositions. So if you transmit the key, and someone else, some secret service, looks at your key, then it gets destroyed. And by trying to decrypt the information you got, which you have in some sense, you will immediately realize that the key has been compromised. So what you can...
But the person that intentionally needs to decrypt it must have the key.
Sorry?
The person who you intend to have
Now, this is the wonderful feature about this quantum cryptography, is that the key is somehow created by quantum physics, say in a kind of black box, and then sort of like it's always done by pairs of particles, and each of you and your partner, you get one of these particles, and actually none of you is actually ever, in some sense, making this key. It's made by a quantum device which is totally random, and you basically are told the result and then you do something with it. This is the beauty of it. But it's really the point that this is why, and if someone interferes with that, this can be observed. There have been protocols being developed where you can then find out whether someone got his fingers into that machine. I mean, ultimately, you're in some sense right that you can, of course, break these codes in the good old way that you will have, say, human traitors. This is always the safest way of getting information. Well. More questions?
One more question. Your first slide where you had the two lines, am I correct to assume that instead of zeros and ones in the normal computing that you can now do 5 different states?
The first slide, it's a bit hard for me to put it up again. Perhaps this wasn't the title slide. Let me see whether I can do that for the others as well to see what was going on there. Let me get back to... Yeah, this was this picture here. So the question was what this actually means. What it means is what we had, this was basically a bunch of these particles aligned in one of these optical simulator experiments where the experimentalists managed to turn around one of them, and then this is sort of like this destroys the structure they would like to have, and then they started dynamics on their own. So your question was whether we can use that to store more information. Well, honestly, yes and no. This is, of course, potentially one of the setups people could imagine using for building a quantum bit, where this would be, say, the 0, and that would be the 1 of a regular bit. But because we have these superpositions, you can have anything in between. This is what creates sort of like the additional degree of sort of like complexity of the quantum computer. But on the other hand, I would be honestly, I would like to say that this particular setup I don't see working as a quantum computer, because the problem is that the experimental control you have to have of these superpositions in a quantum computer is immense. Yeah, and the problem of current technology here is that in which physical setups where you have such a 0-1 situation, in which of these physical setups do you get to the accuracy you need to maintain these superpositions? Because as soon as they get a little bit disturbed, the quantum computer is more or less dead. And this situation on paper could work as a quantum computer. In practice, I don't believe it. Does that sort of answer your question? Okay.
What kind of particles can be entangled? Can atoms be entangled, or is it just particles?
The question was whether any particles can be entangled or whether this is kind of sort of more specific. Well, in some sense, the entire universe, all of us are in some sense entangled between each other. It's just sort of like that if we try to measure it or quantify it, the entanglement between larger bodies will typically be totally negligible in their behavior. I mean, we among us sort of like we behave totally classically. The easiest way basically to get it sort of like exposed and maximize it will actually be for the smallest particles like photons, light particles, electrons, atoms certainly yes, but this is already much, much harder because the atom consists of many, many particles itself. So ultimately I think most of the stuff we are today doing about entanglement is really sort of like individual photons, individual electrons being entangled with each other.
I think we have to
empty the room, I think. Yeah. Thank you very much.